All right, so today's topic is stream ciphers. And stream ciphers are used mainly in communication. In other words, when we need encryption with data in transit. So most of the previous standards in communication were stream ciphers, but nowadays, since we have very fast block ciphers, we also use block ciphers for encrypting data in transit. So let's start. The main idea behind stream ciphers is one-time path. So most of the time people ask if we can create a cipher that is unbreakable. And the answer is yes, you can do it. So idea is as follows. You generate a very long sequence of random bits, zeros and ones. And generally you write it into a small piece of paper in very small fonts. So this is why we call it one-time path, because you're writing it on your notepad. What you do is as follows. You convert your plain text into bits. Of course, you can modify this algorithm and work on characters, but working on bits is easier and better, let's say. So you convert your plain text into zeros and ones. Then you XOR it with the one-time pad, which is you randomly created and gave it to the person you want to communicate. So the result is ciphertext. And the person receives the ciphertext. They also have the one-time pad. Since this is XOR is addition modulo 2, the person gets the plain text back. So here's an example. So for instance, so you add everything bit by bit. So 0 XOR 1 is 1. And when the person wants to decrypt, they receive the ciphertext with 1. They XOR it with one-time pad, obtain the plain text with a 0. So it is like regular addition. Only difference is that when you add 1 to 1, so when you XOR 1 and 1, you obtain 0 and there is no carry bits, okay? So this is the good thing. So here actually the security proof comes from the fact that the one-time pad is random, because once you XOR it, the ciphertext also looks random. If you can capture any plain text bit from the ciphertext, this means that you can also guess the one-time pad bits, which is randomly generated. So one-time pad must be truly random, but also you can only use one-time pads only once. So if you want to communicate with 100 messages, you need 100 one-time pads. So think about your WhatsApp messaging speed. You cannot exchange that many one-time pads beforehand. So actually this is still used. I mean, we know that Washington and Moscow exchanged one-time pads years ago, probably in 1970. So in case of everything gets broken, you can communicate with one-time pad. So idea is fantastic. This is unbreakable, but I cannot use it because it is not practical. So perfect secrecy, ciphertext provides no information about plain text, usually printed on a single page with very small letters, hence the name one-time pad. Instead of working with bits, one can work on letters or characters. Idea of one-time pad leads to idea of stream ciphers. Because the problems are key is too long, because your one-time pad should be at least as long as your message. Key distribution is a problem, and randomness is also another problem. If you don't create your one-time pad in a random way, the attacker can capture your plain text. So this one-time pad uses a long string of key consisting of random bits. The length of the key is same as the message and used only once. Encryption is just combining the key and the plain text bit by bit. Shannon proved that one-time pad is unbreakable. Because of recurring vast amount of key information, one-time pad is impractical. So this summarizes everything I said so far. So stream cipher actually tries to obtain this idea, this security, which is the having random zeros and ones. But stream cipher uses a short key, like 128 bits, and from the secret information, it generates random looking zeros and ones, which we call pseudo-random zeros and ones, and use it as a one-time pad. Okay. So a stream cipher is an encryption mechanism that uses a key stream to encrypt a plain text in a bitwise or blockwise manner. This is important. As you can see, I use the word blockwise because everybody, even in PhD thesis, they talk about block ciphers and stream ciphers. They say that block ciphers encrypt in blocks. So they divide the message into blocks and encrypt block by block. And they say that stream ciphers encrypt bit by bit. This is not correct. This is not the difference between stream ciphers and block ciphers, okay? Because there are many stream ciphers that encrypt block by block or byte by byte and so on. Even the RC4 stream cipher that we are going to talk about soon works on bytes, not on bits. Okay. So then you will ask, what is the difference? And I will say the difference in a minute, but the main idea is that Steam Ciphers has some kind of a memory, a state, and that state changes in time. Block Ciphers does not have that kind of structure. Okay, so we can divide Steam Ciphers into two parts. Synchronous Steam Ciphers, key stream is generated from only the secret key and the initialization vector. Okay, so everybody, the person you want to communicate also has to be synced with you. So if the synchronization is lost, you lost the communication. But there's also asynchronous stream ciphers, also called self-synchronous stream ciphers. Key stream is generated from the secret key, IV, and some past ciphertext bits or bytes. Okay, so even if you lose the synchronization due to bit drops, bit modifications, or bit additions, you will lose the synchronization. But after some point on, if you keep getting ciphertext bits correctly, since your internal state will be determined by these bits also, you will get the synchronization back. Okay. I will talk about synchronization later. So, symmetric key crypto systems are classified as block ciphers and stream ciphers. We talked about block ciphers before. Block ciphers operate on large blocks of plain text data with a fixed transformation. This is the keyword here. So think about AES, DES, and so on. There is a fixed transformation. The cipher is fixed. Stream ciphers operate on individual plain text digits with a time-varying transformation. Okay, because they have kind of a memory, a register, an internal state, and that changes depending on time. So encrypting same plain text would not give you the same ciphertext once you change it, change the time, and so on. Okay, so let me make it even more clear. A block cipher processes the plain text in relatively large blocks at a time, and the encryption function is same for every block. A block cipher can be considered as a bijective function, which takes the plain text and the secret key and produces the ciphertext. Okay. Some mode of operations can turn a block cipher into a stream cipher. We already talked about them. Think about counter mode. It actually, instead of encrypting plain text, it encrypts counters, obtains a key stream, and then XORs it with the plain text. So this is, as you can see, it works like a one-time pad, but the one-time pad in this scenario is not randomly generated. It is pseudo-random because you're obtaining it from block cipher encryption. A stream cipher processes the plain text in small blocks, sometimes as small as a single bit. Contrary to a block cipher, a stream cipher has a sort of memory. This state, which I wrote as row T, at the time of T, it is in the state of row, as it processes the plain text. So it changes as you keep encrypting the plain text. This state is an input of encryption algorithm. We can consider stream cipher as a pair of functions f and h as next state function f actually takes input as the current state, current plain text, and secret key, and produces the next state. Of course, sometimes you can remove plain text from here. But the output is, depending on your current state, plain text, and the secret key, you perform some operation and produce the ciphertext at time t. Okay, so this can be, H can be as simple as an XOR operation, but you can do something more complicated if you want. So I mentioned that from a small secret key, I want to produce something longer that looks random. So how you can use a small information and generate something longer? So linear feedback shift registers are one of the common ways used in stream cipher because it's really fast. It doesn't require anything. But the idea is as follows. Maybe I wrote it also sentences. We can read from the sentence and explain it on the figure. So LFSRs are very common in stream cipher designs. At one tick, one clock, the register produces one bit output from here. So actually, generally, it produces this value as an output. Okay, so this is, removed from here and sent as an output. State is shifted one bit. So since you remove this from here, everything from here is shifted to here. So you end up with an empty place here. So all of these boxes represent zeros and ones, so they're in bits. So state is shifted one bit, and the new bit is obtained by the XOR of bits of the previous state that has a tap point. So here are tap points. Assume that maybe we don't have these tap points, but only this one and this one. This means that in the next state, this bit is XORed with this one and becomes the next value when you shift everything to the right. So an n-bit LFSR can have at most 2 to the n-1 different states. This is the important thing. So assume that you have 8 bits here. So internal state can have 2 to the 8 different values, right? I say -1 because if you fill everything with zeros, XORing everything again will give you 0, so it will produce zeros infinitely. So this is why I'm removing 0 here. So this internal state can take 2 to the n-1. So if it is 8-bit, you can have 2 to the 8-1, which is 255 bits, right? So from 8 bits, you generate random looking 255 bits. But this is exponential. So if you get like 10 bits here, then your LFSR can produce 1023 bits. But after that, it will repeat itself, which we call period. Yeah, thus it repeats itself after 2 to n-1 bits. We call it period. Maximum period is obtained when the tap points are chosen according to a degree n primitive polynomial. So we think this as a polynomial. So if it is 8 bits, you write it as a degree 7 polynomial, and depending on the primitive polynomial, if the constant in front of the monomial is 1, you put a tap point here. This is how you get the maximum period. So you can, add something, and instead of 2 to the n-1, your LFSR might produce something less than that. This is why we work on primitive polynomials and so on. So let me show you an example. This is A51, GSM standard developed in 1987. I think it was kept secret initially, but since you put it into every device, every mobile phone, it is easy to reverse engineer. But as you can see, it is a very, very simple design. So we have 3 LFSRs. So at one tick, this LFSR produces output, and you just XOR them as the output. So if you think about this, this is very easy to implement in hardware. So there are in total 64 bits here. So the secret key is also 64-bit. You feed here, and actually we will talk about it in the future, but these are also used as the majority point, which determines which LFSRs will be used in everything, okay? But the bad thing is that this is very easy to break. So we can actually listen every 2G GSM communication when they use this, okay? So you can create a very small device yourself, put it into your backpack, walk around and listen every communication if they are using this. So this is the important part, but we will talk about it when we talk about dedicated stream ciphers in a minute, okay? So, but here the idea is that here you are producing key stream. When you're talking on the phone, your voice is turned into a plain text as zeros and ones. You XOR it and send it to the person. That is the idea. So, key stream. It may be the case that the next state function does not depend on the plain text. This is generally the case, by the way. In such a case, a key stream is produced by an output function G, and the encryption function combines the key stream with the plain text. So in the next state function, we no longer depend on the plain text, and the output function simply uses the current state and the ciphertext. So encryption function is just H here, but again, most of the time, this is simply an XOR operation. This type of stream ciphers are known as key stream generator ciphers. They have the advantage that the key stream can be pre-computed without using the plain text or ciphertext. So actually, this is what you can think about using AES in counter mode, right? You can encrypt your counters, obtain the key stream, and wait for the plain text to come. When the plain text arrives, you can simply XOR it and produce the ciphertext. So stream ciphers work like this. An important example is the binary additive stream ciphers, where H is bit-by-bit addition of the key stream and the plain text. Here, this means that you simply XOR the key stream with the plain text. Block cipher mode of operations like counter mode actually converts the block cipher into binary additive stream ciphers. Okay.